This is a video for AQA Further Pure Mathematics, Sequences and Series, Section 2.4. We're using induction to prove results about series. Well, the first example I'm going to look at is to prove the result that the first n square is equal to n over 6 multiplied by n plus 1 to n plus 1. So a standard result that we've met before. Well, the process of induction has the three steps, as we're well aware now. So in the first case, what we need to do is to check when n is equal to 1. So on the left hand side, we've got the sum from r equal to 1 to 1 of r squared. So of course that's just equal to 1 squared, which is equal to 1. And on the right hand side, we have 1 over 6 multiplied by 1 plus 1 multiplied by 2 multiplied by 1 plus 1. And if you calculate that, you've got 1 over 6 multiplied by 2 multiplied by 3, which is also equal to 1. So therefore it's true for n equal to 1. Well, the next step is to assume that it's true for n equal to k, in other words that the formula with value of k in it is in fact the sum of the first k square numbers. And then we've got to say, well, what do we need to do then to show that it's also true for n equal to k plus 1? So we need to show therefore that the sum from r equal 1 to k plus 1 is then going to be equal to k plus 1 over 6 multiplied by k plus 1 multiplied by 2 times k plus 1 plus 1. So this is what we need to show. Now it's worth doing that so that we've got some idea what it is we're aiming for, and see if you calculate that expression that I've just written down, then it's 1/6 k plus 1, k plus 2, 2k plus 3. Well, let's look at the expression for sigma r squared then from r equals 1 up to k plus 1. With anything like this, we can always write it as being the sum from r equal to 1 up to k of r squared, and then plus the next term, and of course the next term is k plus 1 squared. But we're assuming that we have a formula for sigma r squared up to k as being equal to 1/6 k, k plus 1, 2k plus 1. And then we've got plus k plus 1 squared. Now with this type of expression you should always factor out as much as you can. The common factor k plus 1 and also 1/6, so that our factor 1/6 multiplied by k plus 1 is going to come outside the bracket, and then inside the bracket we'll have everything that's left, so that we get k multiplied by 2k plus 1 from the first part of the expression, and then we've taken 1/6 k plus 1, so we have to think about 1 as being equal to 6/6, so the second part of the expression will be 6 times k plus 1. Now if you multiply out that square bracket, you get 1/6 k plus 1, and then in the square bracket we've got 2k squared, a total of 2k plus 6k, I beg your pardon, a total of k plus 6k, which is 7k, and then plus 6. And that quadratic expression factorizes as being equal to k plus 2 multiplied by 2k plus 3. And of course that was the expression that we wanted. So it's worth writing it out with k plus 1 and saying this is equal to 1/6 of k plus 1 multiplied by k plus 1 plus 1 multiplied by 2 times k plus 1 plus 1. In other words, it's true for n equal to k. So what we've done, we've shown that if it's true for n equal to k, it's also true for n equal to k plus 1. And then we can finish off by saying, as it's also been shown to be true for n equal to 1, it's true therefore for all n. We should really say that these were values of integers or natural numbers, so all n, which remembers the natural numbers. Now a question involving sequences, a sequence defined by an inductive definition, which is un plus 1, where the next term is 4 times the term before minus 6, so 4un minus 6, and we're told that the first term is equal to 3. And what we want to show is that the general term, the nth term, is then equal to 4 to the power n minus 1 plus 2. And we want to do that by induction. So again, the 3 steps. The first step is to look at the case when n is equal to 1. So when n is equal to 1, we can see that u1 by our formula would be 4 multiplied by 1 minus 1 plus 2. That's 4 to the power 0 plus 2. And that's equal to 3. So it's true for n equal to 1. We do indeed get the correct first term. The next step then is to assume that it's true for n equal to k, in other words that uk is equal to 4 to the power k minus 1 plus 2, and then to show that that means that it would also be true for the next value u to k plus 1. So that will be equal to 4 to the power k plus 1 minus 1 plus 2. Now to do that we need to use the inductive definition that we've got at the top. So we can say that uk plus 1 must be equal to uk minus 6, 4uk, I beg your pardon, 4uk minus 6. So using this definition here for un plus 1. But we're assuming that our formula is correct for uk. So substituting that into here, uk we're assuming is equal to 4 to the power k minus 1 plus 2. Now when we multiply that out, we get 4 to the power k plus 4 times 2, so plus 8 minus 6, or in other words it's 4 to the power k plus 2. Now we want to write this in terms of k plus 1, so this is 4 to the power k plus 1 minus 1 plus 2. In other words, we've shown that if true for n equal to k, it's also true. So that implies that it's also true for n equal to k plus 1. We'll put that together with the fact that we know that it's also true for n equal to 1, and therefore it's true for all values or integers greater than or equal to 1. Well, that's the end of this video on induction for series, and indeed it's the end of the section on sequences and series.